Hello, welcome back to this course on structure, stereochemistry and reactivity of organic molecules and intermediates, a problem solving approach. In the last episode, what we are discussing was the application of an empirical rule, which is octant rule, in determining the stereochemistry of a molecule. Now, stereochemistry of a molecule means the study of its conformation or configuration, as the case may be. Okay. Now, you remember what was this octant rule is applicable to determine or to predict the sign of the Cotton effect. Okay. Now, the Cotton effect is basically the anomalous behavior that is shown when the wavelength of light is decreased and you measure either the refractive index, that means what is called the circular birefringence, or you can measure the ellipticity, because when there is differential absorption the light becomes elliptically polarized light. So, either this ellipticity you measure against decreasing wavelength or the refractive index, the difference of the refractive index between the right and the left circularly polarized light. Okay. Which can be expressed in terms of a rotation or a molar rotation or specific rotation, and you see that the what happens that the there is first there could be this anomalous behavior, basically that there could be a maxima first, that means the rotation can increase to a maximum and then followed by a rapid decrease and it reaches a minimum and then again goes up. The same may happen with also in case of the circular dichroism. Okay, where the ellipticity goes up and then goes down and then again goes up. Okay. So, depending on whether you reach the maximum first while we decrease the wavelength and minima followed by the minima, that is called the positive Cotton effect, and the reverse is what is called the negative Cotton effect. Okay. Now, this Cotton effect is basically an experimental measurement that one can measure the sign of Cotton effect exhibited by a chiral molecule with a chromophore, and again I repeat, the Cotton effect is shown and in the window of the absorption of the chromophore. Okay. Now, there are different rules, empirical rules. First, we have discussed the axial haloketone rule, specifically the two axial haloketone rule, and then we introduced to you the octant rule. Okay. Just a quick recapitulate that what is this octant rule all about. The octant rule is basically that you place the cyclohexanone in such a way which is shown here, this cyclohexanone system, and this carbonyl. So, you basically it is a three dimensional space. So, you divide the three dimensional space by three planes, namely the xy, the xz and the yz plane. So, one plane is basically which is shown here, one plane which is the, if you think that this is the z axis, this is the x axis and this is your y axis. The y axis is going somewhere through here. Okay. So, so these three planes basically segment the space into, first of all, into front and rear octants. Now, what are those? That if you have the carbonyl on this side and if you view the carbonyl from this side, then this plane is basically dividing the space into two. One is which is away from the observer and the other is which is lying on the side of the observer. So, if it is away from the observer, then so we are talking about the xy plane. If it is lying behind this xy plane, then that will be called the rear octants, and the plane which is in the side of the observer, the viewer, that is the front octants. Okay. Now, that is the first division, and then the second division of the space is basically done by this plane, which is the xz plane, and by this what you have done, you have actually if you think of the rear octants, you have dissected the rear octants now into a left towards the left of the observer and towards the right of the observer. Two spaces are created. The same is true for the front octants. Okay. You are dividing the front octants into towards the left space and towards the right another space. Okay. And then employing the third plane as is shown here, this third plane will divide again the left and the right again into two spaces. Okay. So, basically what you have 4 spaces at the back, that is in the rear, and 4 spaces in the front. Okay. So, this is basically what are called the octants. Okay. In 2-dimensional figure we have quadrants when you employ 2 axes or 2 planes, perpendicular planes. Here there are 3 mutually perpendicular planes, and that will divide the space into 8. So, that is octants. Okay. And these octants, 4 of them will be behind the observer. The observer is basically looking in the line of the oxygen carbon bond and from the side of the carbonyl oxygen. Okay. So, that will put that rear octants and the front octants. So, if we look at the rear octants, so this is so something at this point, that means it goes into the if you are thinking that I am standing here. So, my left side will be on this side and my right side will be on this. Okay. So, this will occupy to the left. So, rear left, and any group here on this side will occupy the rear right. Okay. So, and then because of these other plane, that means this plane which is the this is the, see, the planes are basically, this is x z plane, this is x y plane, this is the y z plane. So, this y z plane, some space are actually above this y z plane, some are below the y z plane. So, depending on that, we will call this as the lower, this is called not the lower, because it is actually above this y z plane. So, this will be upper left. So, this space will be called upper left, and something which is here below this y z plane, that will be, and also on the right side will be called the this is, say, first of all lower. So, this will be lower right. Okay. So, this will be lower right. So, depending on that, basically you have basically now in the rear octants you have a lower, this is lower, this is upper, sorry, this is upper right, this is upper left, and this is lower left, and this is lower right. Okay. And the contribution of a substituent, which is depending on which octant it is actually, which octant this is occupying, that is important. Okay. And if you look at the sign of the axis. So, if it is plus x minus x, then plus z minus z, and this is plus y minus y. And so, any substituent on the lower on the upper right. Okay, let us see what is upper right. Upper right is basically on this side. Okay. So, upper right will have, so the upper right, the contribution of the substituent will be plus x, because that is the sign of the coordinate here, x coordinate, then plus y and minus z. You can actually look it from here, something which is on this side, something which is on the upper right. Upper right will have plus x definitely, upper right will have plus y, okay, because it is in the right direction, and minus z. So, if you multiply these contributions, then what will happen? You will get a sign of minus. Okay. So, that is why this contributes in a negative sense. That means, any substituent in the upper right rear octant will contribute in a negative fashion to the sign of the Cotton effect. So, similarly, you just carry on with the sign of these axis if something of these basically the coordinates and multiply them, and that will give you the contribution, the sign of contribution towards the cotton effect. So, if you think of upper left, in upper left your y is negative, your z is negative, but your x is positive. So, multiplication of this will give positive positive cotton effect. Okay. So, that is how it is. Now, it is purely empirical, but interestingly this empirical rule works. Okay. There are some different empirical rules, you know, that this Woodward as a Dine rule for calculating the lambda max. Okay. So, those are basically empirical rules which are derived by looking at several molecules, like Woodward did look at the lambda max for several dienes and then came out with his famous Woodward's Dine rule, okay, and then dinophile rule. Similarly, by looking at the sign of cotton effect of several ketones, then people have come out with this octant rule. Okay. So, this is for the rear octant. Remember, in the if something is on the front octant, then this sign of cotton effect, contribution of cotton effect will be just the opposite. That means, if it is the front octant, then upper right front octant will contribute in a positive sense. Okay. So, this is your upper right rear octant. Okay. This is your lower right upper right, sorry, this is upper left, I am sorry, this is upper left rear octant, and that contributes plus. So, if it is in the the front octant, then upper right will contribute positive. That means, it is just the reverse of all this. So, you have to remember that. Fortunately, most of the molecules that that are there, that have been studied, have their substituents mostly falling in the rear octant, but there are some cases where substituents can also come in the front octant. Okay. And then you have to be careful. Just remember that it is just the opposite of what is the sign of contribution for the rear octants. Okay. Now, let us decalone system or even cyclohexanone system, simple system, and applied the octant rule. Okay. Let me just, and then let us take little bit more complicated cases. Complicated cases means where the number of cyclohexane rings are more. Okay. Now, remember, you should always be very confident in your original understanding of a cyclohexanone axial equatorial bonds, because what you are doing in octant by applying octant rule is basically taking a projection on a screen which is held at the rear side, and you take a projection of all the substituents of all the atoms onto that screen. Okay. And you should have very clear idea of how the projection looks like for a cyclohexanone system. Let me just draw it here, the projection again. So, if it is the carbonyl, sorry. So, if this is the case, this is the carbonyl. So, this is 1, 2, 3, 4, 5, 6. Okay. So, at this, so when you take the projection, then what will be the projection diagram look like? See, 1 is in the central point, you are looking from this direction. So, 1, then on the right is 2, on the left is 6. Okay. Here there is one important point, that when you talk about a cyclohexanone system, the carbonyl, when you look at the carbonyl, you should make sure that the carbonyl carbon is occupying the head of a chair. You know, the head of a chair means in the chair there are certain 3 carbon atoms which are actually called the head of the chair, like these 3 ones. Okay. And these are the leg of the chair. Okay. So, the carbonyl has to occupy the head of a chair, which is it is occupying the way I have written here. The carbonyl is occupying, because this is a head, that is a head, and that is the head of the chair. Okay. So, carbonyl is in the right position. Then you look through the oxygen carbon bond. Okay. And as you look, you will see that 1 is in the middle, then 2, then 3. On the right side gets 2, on the left side gets 6, and then it goes up. Okay. 5, and then 4, and 3 and 3 is connected to 2. Now, the cross section of the two planes, okay, of the two planes, which is basically, I can go back, no, I think that is okay. The cross section of the two planes, which is basically dividing into these 4 spaces, the rear, the 4 spaces at the rear and 4 spaces at the in the front, their cross section of the two planes will be lying like this, 2 lines perpendicular, mutually perpendicular to each other. Okay. And that means one plane is going through this line, one plane is going through this line, okay, and the other plane is going through this line. So, this is the basically the picture. So, what we are drawing is the intersection of the two planes and the projection intersection, which is drawn as a projection. Okay. So, now, so this is the basic diagram you should remember, okay. And then the substituents, because everywhere there is an equatorial and axial substituent. So, you have to be careful which way these equatorial and axial substituents go. So, what happens actually, the equatorial is going in the horizontal direction and the axial goes in the vertical, along the vertical direction, okay, up or down. So, equatorial, 2 equatorial will be on the right side and 3 equatorial will be also on the right side, and then 3 axial will be on the upper side. Okay. Remember, these, when you have completed 3 lines, the 4th is automatically fixed, the 4th group, the projection of the 4th group. So, when you know that the equatorial is on the right, so that means their axial has only one position here, that is the top. Okay. For the 4th carbon, which is incidentally lying in the right in the plane, which plane, that means this is the plane, or which is lying actually at the cross section of the two planes. So, this 4 has an axial, 4 has an equatorial here and axial there. So, you can make out from this, I think it is easy to visualize that the equatorial will go up and the axial will go down. So, this is the scenario, and then 5 and 6. So, 5 equatorial is on the left and axial on the right, and then 6 equatorial on the left and axial on this. That means, this axial is occupying the lower right. Okay. These are occupying the upper right and these are occupying the upper left and this is lower left. Okay. So, that is the scenario, and this you have to be you have to remember, at least you have to understand this, how to draw this equatorial axial, because when you have more rings, then this is important, because the ring bonds will be either axial or equatorial. So, you must know how to draw this. Okay. Now, let us come to this system which is depicted here. This is the parhydrophenanthrone. Okay. Now, as I already told you that this Cotton effect, this octant rule is utilized to know the conformation configuration of a molecule. Another important point is, suppose you have a cyclohexane system where you really do not know the structure, the basic structure. Basic structure means the constitution. Constitution means you should know the connectivity of different atoms, and sometimes what happens, you are not very sure where is the carbonyl, whether it is at the C1 position or C2 position. So, the precise location of the carbonyl is also very important to know, and it is also can be determined with the help of the sign of the Cotton effect. Okay. So, now there are 3 things that you can know precisely: the location of the carbonyl, the conformation of the system, as well as the configuration. Okay. All these 3 can be verified with the help of Cotton effect, sign of the Cotton effect. Okay. Now, let us take a molecule which is parhydrophenanthrones. Not only parhydrophenanthrones, you have already read different parhydrophenanthrenes, and different parhydrophenanthrenes are expressed in terms of the stereochemistry of the ring junction and the relation between the hydrogens, which are not ring junction hydrogens, that means between the A and the C ring, the hydrogens, what is the spatial relationship. Okay. That is expressed as transoid or cis-oid, and the ring junction are cis or trans. Okay. So, here it is a molecule, like this molecule is written here, this molecule is written here. This is what is that? This is trans, this is first of all 5-10 ring junction is trans, then 10 and then this is 9, that is not written here, this is 9. So, 10 and 9 they are transoid, and then 9 and 8 are again trans. So, this is a transoid transphenan parhydrophenanthronones. Okay. So, you have a carbonyl. Okay. Now, here the question is that if you have a carbonyl at the 2 position of this system, then what will be the sign of the Cotton effect. Okay. Now, the sign of the Cotton effect has already been experimentally determined that it is positive. Experimental is positive. So, if this structure is correct, suppose you have a parhydrophenanthrinone, and if you want to really know whether the carbonyl is at the 1 position or at the 2 position, then determine the sign of the Cotton effect and then predict it with the help of Octant rule, and then see what was the experimental observation. Okay. So, let us draw the projection of this in the octants. Okay. The octant projection of these 2 parhydrophenanthronones, okay, in the transoid trans isomer. Okay. So, this is the situation. Now, what is actually done in octant, in drawing the octant projection, that you have to look along the oxygen carbonyl, oxygen of the carbonyl and the carbon of the carbonyl, that means OC bond, okay, against the OC bond or along the OC bond, sorry, along the OC bond. And then, but you have to make sure that you are looking at the carbonyl carbon when the carbon is occupying the head of a chair. Okay. So, in this case, there are, first of all, this is occupying the head of a chair, that is not a problem, because these are the head of the chair, sorry, this one, that one and that one, that means C10, C4 and C2. So, that is first condition is met. The second condition is that you have to look along the OC axis. However, here because the carbonyl is on the other side, so it is very difficult that you stand here and then look at this, look along this OC bond. Okay. So, to simplify the problem, because the way to do it is that you have to turn it upside down. Okay. You have to turn it upside down or turn it in such a way that it comes in front of the observer. Okay. Otherwise, the observer has to stand here. Okay. The observer has to stand here. What I usually do, I suggest to the students is that whatever way the carbonyl is written, let it be there, and you also you are comfortable by looking from this direction, because you are on the you are actually lying top of the, you are seeing from this side, from the top of the screen. Okay. So, you look from this side, the carbonyl is occupying the head of a chair, but you are looking just opposite to what is required for drawing the octant projection. If that be the case, then what happens is very simple logic, that if you look from this side, whatever comes to the right, that will go to the left, and whatever was in the left, that will go to the right. So, that is the simple logic. So, if you do that, then you know that 2 is in the central point, and then as it appears that 1 is on the right, but then actually it should be on the left. 1 should be on the left, and then 3 should be on the right. Okay. And then once you fix that, it is not a problem. Now, 1 is connected to 10, 1 is connected to 10, 10 is connected to 5, okay, and 5 is connected to 4. So, this is the projection of the ring A containing the carbonyl. Okay. So, this is your the cross section of the 2 planes, okay, the intersection of the 2 planes, and now you have to complete the other rings, the projection of the other rings. For that, you need to know where are the carbonyls, where are the axial and the equatorial bonds. Okay. Now, before that I should have mentioned here that how the contribution of the each substituents vary depending on their location. Okay. First of all, substituents or atoms which are lying along this axis, they do not contribute at all to the sign of the Octant effect. And the substituents which are, and the sign is obviously determined at which octant it is occupying, that is we have already told, but what will be the extent of their contribution, that depends on how close it is in towards the how close it is in comparison to the chromophore. So, if the greater the closeness, spatial closeness, so it will contribute more. Okay. I think I have certain, let me see, maybe I missed that. Yes, first of all the carbons which are occupying mirror image positions, okay, they cancel each other. The substituents which are occupying mirror image positions, they cancel each other. Okay. And as I said that the substituents which are lying, or atoms lying at the basically in one of the planes, like this plane or that plane, or I can say that the projection is right on this the axis is created by the intersection of the two planes, then they do not contribute at all. Okay. So, these are the important points. So, that means 4 will basically cancel the contribution of the 10, because both are carbons. So, they will contribute, they will cancel each other. Okay. But let us continue to draw the projection. Okay. So, this is the first ring, that means the cyclohexanone, and then 10 has a 10, you know that equatorial goes in, sorry, the equatorial goes in this direction. So, what is the equatorial bond in attached to 10 is 9. If you look carefully, 9 is equatorial to this ring A, if it is the ring A. Okay. So, that is equatorial, and the other is basically the 5. Now, the 5 you have the remember 2 and 5, the plane which is going through 10 is also going through 5. So, 5 your equatorial is at the top. So, equatorial means this is 6. Okay. So, that will be 6, and so 9, 10, 5, 6, because that is the equatorial one, and axial goes at the bottom, if you remember the original diagram. Okay. And then once you fix 4 atoms, then it is easy to complete the full picture. So, 9 is attached to 8, you do not have to think much in fulfilling the other atoms. Okay. 7, and then that is connected to 6. So, this is the ring B, and now the ring C. So, this is suppose B and the ring C. So, ring C starts from what? Ring C is fused to 8 and 9. So, you have to see what is the 11 carbon atom, that bond 9-11 bond, whether it is equatorial or axial. It appears that it is equatorial. Okay. The bond which is attached to 9, that means the 11 attached to 9 is equatorial. So, 11 will be here, and then 8, what about the 8? 8 also has an equatorial carbon, which is carbon 14. So, 8 also equatorial. So, equatorial will go on this side. So, that will be here 14. Okay. Now, you have 4 atoms already fixed. So, you can complete that. Okay. 14 is attached to 13 and 13 is attached to 12. Okay. So, this is the complete diagram. Remember, do not forget the 2 axes. Okay. So, this is the axis. So, now you see although 4 cancels 10, the contribution of 4 cancels 10, but you have a huge number of other atoms which are not cancelled by any. Okay. There is no atoms other than 4 on this side. Okay. So, basically you have a strong, you expect that it should show a strong positive Octant effect. And what was the result? Yes, it indeed showed a strong positive Octant effect. So, that is how you draw the projection and then do the confirmation of the position of the carbonyl, because that immediately proves that yes, the carbonyl is at the 2 position. Let us just quickly do the 1 one, because 1 one is a little bit more tricky. Here the carbonyl carbon is occupying carbonyl carbon is occupying the leg of a chair, okay, the leg of a chair, and also it is on the opposite side of the observer's view. Okay. Otherwise, observer has to go on the back side, which is very difficult here. So, or you can turn it upside down. What has been done here, that turn it upside down, that is one way to do it. If you turn it upside down, the advantage is that the leg of the chair becomes head of the chair. Okay. So, you satisfy that one, not only that one, you also satisfy, you also make it very comfortable for the observer to see from the oxygen carbonyl bond. Okay. So, the other way is basically you do not turn it upside down, you do not change the structure as it is represented. Okay. On the other hand, you just make a logical, you just put some logic behind your drawing the octant projection. Okay. So, what we do, like last time for the 2-on what we did, we looked at the opposite to the oxygen carbon bond, but we are looking from the carbon oxygen bond, because that is the basically the from the side I am looking at. Okay. So, I look from this side. Now, while I look from this side, I am violating the direction parameter. That means, I am supposed to look from the oxygen carbon direction, but this is I am looking from the carbon oxygen. Okay. So, that is one violation. The second one also is the carbonyl carbon is occupying the leg of a chair. So, there are two variations here. Okay. Unlike in this case of the 2 ketone, where there is only one variation, that I am just violating the direction parameter. Here I am violating both the direction parameter as well as the head carbonyl carbon occupying the head of the chair. If that be the case, then I do not have to change anything. Whatever I see from here, right will remain on the right side, left will remain on the left side. So, that is the logic that one can put forward while drawing the projection in the octant projection of this molecule without disturbing the molecule at all. Now, it is up to you what to do, which one is comfortable, whether you turn it upside down, bring the carbonyl carbon to the head of the chair, and as well as also bring the carbonyl facing the observer. Okay. So, that is one approach, but let us adopt the second approach, which is kind of a mnemonic approach, put some logic. Again I repeat, if there are two violations, then you do not have to change the right left. Okay. So, let us draw the projection. This is 1 and 1 is connected to 10, that is not a problem, and 1 is connected to 2, that is also okay. Then you have 3, then you have 4, then you have 5 and you have 10. So, this is the A ring. Okay. Remember, this is the axis, 2 axes. Okay. Now, 5 is connected to 6 and 5-6 bond is equatorial. So, that will be here 6, and 10 is connected to 9 and 10-9 bond is also equatorial. So, 10-9 and then 6, then as you have 4 atoms already fixed. So, you can complete it, that 6 is connected to 7, 7 is connected to 8 and this. Now, there is another interesting feature of this molecule, that you can also, this interesting feature can be visualized or can be understood by looking at the molecule. See, when you divide this space around the carbonyl into the rear and the front octants. So, the plane that was dividing it into the two rear and the front is basically this plane, okay, the plane which is going through this. So, this is the plane which is dividing it into rear and the front octants. If you do that, you see that we should observe from this side. So, this will be 3, 4, 5, 6, 7, they will fall in the rear octants. But what about this 11, 12, 13? As you see that will be on the towards the side of the observer. So, that will be in the front octant. So, that is another important change here, okay. And you will face that, you can show it here, that let us complete the C ring now. So, B ring we have completed. So, 8 is connected to 14, 8 is connected to 14 and via an equatorial bond. So, that is not a problem, but now the other joining is 9 to 11. 9 to 11 is equatorial, but it is unlike, it is not going into the rear octants. Okay. So, it is actually coming in the front octant, and that will be, there is a way to show the front octant, means there are, you have to remember, I put circles, I may put dark circles, of course, you have to put the numbering here, that is 11, and then another dark circle, that is your 11, then 12, and then 12 is connected to 13. So, these three are residing in the front octant. Okay. As you can see from here also, if you dissect it like this with this plane, you see that 11, 12, 13 are in the front octant, and that is what is happening here. Okay. So, this is the situation. So, if that is the situation, then now 3 can cross out 5, they are in the mirror image positions. However, there is 6 and 7, 6 and 7 contributes because they are in the rear octants, and upper right, that they contribute in the negative sense. Okay. That is okay. And now, what about this one, which is occupying the lower right of the front octant. Now, remember, in the rear octant, this is minus, that is plus, this is minus, that is plus, and in the, so this is rear, and in the front octant it will be just the opposite, minus, plus, minus. So, this is occupying the lower right of the front octants. Okay. And so, that will also have negative contribution towards Cotton effect. So, the overall it should show the molecule, this 1 on should show negative Cotton effect. Okay. And that is the case, it showed the negative Cotton effect. Okay. So, you see that sometimes things are little difficult, little tricky, especially when the carbon atoms come into the front octant. But I will always suggest to do this check, that when you have the carbonyl, put a line like this and see if anything is coming behind, coming in front of the line or behind the line. Nothing is in the front. So, there is no atom in the front octant for this molecule, but for this molecule, when you draw this line, you see that 11, 12, 13 are actually on the side of the observer. So, that comes in the front octant. So, that gives you first indication that okay, when I draw the projection, I have to keep that in mind, that some atoms are actually in the front octant. And the other thing, you just remember this, the contribution of the substituents in the rear and the front octants. Okay. So, I think these examples will clear your doubt or has cleared your doubt. Practice it more and more, because there are even more complicated cases which are called which are steroid. That means, there are 4 rings and 4 ring systems, your drawing could be little trickier than this, and I will show one molecule here which is a steroid. Let me see, the molecule may be drawn here. This is again a parhydrophenanthrene. We can come back to this in the, maybe in the problem solving session. We will do problem solving in the next lecture, and then at that point we will bring in the steroid molecule, and then we will do some projection practice of how to draw the projection, and then how to predict the sign of the Cotton effect. Okay. Thank you.